Okay, now we got to take kind of an account where we were and get our bearings about us. In the first part of this lesson, we were always starting off with some type of a parallelogram and then proving a characteristic about it. Given a parallelogram, prove that the diagonals bisect each other. Given that we know it's a parallelogram, prove that the opposite angles are congruent. Given that it's a rectangle, prove that its diagonals are congruent. Given it's a rhombus, prove that its diagonals are perpendicular to each other. So that's the kind of thinking that we've been in. And now we want to turn our thinking around a little bit in a reverse process. So this is about what are sufficient conditions for us to be able to verify that it is a parallelogram. So the difference is, before we knew it was a parallelogram, we found some characteristics that had to be true about it. In this part of the investigation, we're going to start with the understanding that we have a quadrilateral. We don't know that it's a parallelogram. Are there some conditions that will verify and prove that it has to be a parallelogram? So we're always going to be starting with the quadrilateral, which means we're starting with a four-sided figure. And if this four-sided figure has these specific characteristics or traits, then does it force the four-sided figure quadrilateral to be a parallelogram? So in every one of the proofs from here on out, we're trying to prove that it's a parallelogram. And if it's going to be a parallelogram, then we would know that its opposite sides are going to be parallel by definition of a parallelogram. So here's our thinking on these. We've got to think in reverse. And let's take a look at the first example. So what if we had a diagonal of a quadrilateral that divides it into two congruent triangles? Then does the quadrilateral have to be a parallelogram? So the question is being asked, is this going to have to be a parallelogram? So what are we starting off with? The first thing that we know that we start off with is that we have a four-sided figure. So I got A, B, C, D. Now I have a representation of a figure on the board, and obviously it looks like a parallelogram, but yet I don't know that it is, so I'm just saying A, B, C, D is a quadrilateral. That's as far as I can go from the given statement. The second part of this given statement is, it says it divides it into two congruent triangles. So what if it divides it into two congruent triangles? So you put in one of your diagonals, and what the given statement is saying, it did create two congruent triangles. If that's the case, does this have to be a parallelogram? So we're also knowing, because we throw a diagonal in there, that triangle ADB is congruent to triangle. If I go ADB, then A matches C. And if I'm going to do that right, then it's got to go CBD. That was also given. So what we're really looking at here is some given situations where they're telling us, number one, it's a four-sided figure. If we draw one of our diagonals in, then these two triangles have to be congruent. Now the very fact that they're congruent can help us with some of the corresponding parts. Now the idea is we want to prove it's a parallelogram. If I want to prove that it's a parallelogram, then I have to make sure that opposite sides are parallel. The only way you can prove that sides are parallel is by forcing it through angle relationships. And in particular, we want to look at some alternate interior angle relationships. So I'm going to highlight a few angles, angle 1 and angle 2. I know that angle 1 has to be equal to angle 2 because D and B are corresponding parts of congruent triangles. So I know they're congruent, and they also have to be on the interior sides of the lines DC and AB, and on the alternate sides of this transversal. So they are alternate interior angles, but these alternate interior angles are congruent, so therefore the lines will have to be parallel. So we have those angles that are going to force those two lines to be parallel. The other angles, angles 3 and 4, they are also congruent because they are corresponding parts of congruent triangles, but they form the other alternate interior angles that forces AD and CB to be congruent. So therefore, this has to be a parallelogram because the opposite sides are parallel. So in my proof, I'm going to record the information we just talked about. I know that angle 1 has to be equal to angle 2 because of CPCTC. Now this is a really critical point. The only way that I know 1 and 2 are equal is because I knew that the triangles were congruent. So this thought is something that really kind of hangs people up. They don't do it in the right order. We know that they're congruent through CPCTC. That tells us that DC has to be congruent to AB by our alternate interior angle theorem that said if your alternate interior angles are congruent, then the lines must be forced to be parallel. We're going to use the same analogy and say that angle 3 had to be congruent to angle 4 because they were also corresponding parts of congruent triangles and were congruent. But if those angles are congruent, that forces the lines AD to be parallel to, I think I looked up here and I looked in statement 4 and I can see an error that I made in recording that. I wasn't really trying to make them congruent, I was trying to make them parallel. So let me fix that. And as I was writing the other one down, I noticed I had that in there wrong. AD is parallel to CB by our alternate interior angle theorem again. Now I can say for sure that ABCD is a parallelogram by definition of a parallelogram. Okay, so what we're saying in this proof is anytime that we create two congruent triangles, when we draw the diagonal in a quadrilateral, it's kind of a mouthful, but remember we started off knowing that we had a four-sided figure, we drew in a diagonal, and if those triangles are congruent, then it is going to force that quadrilateral to be a parallelogram every single time. So this is what is called a necessary and sufficient condition for it to be a parallelogram. So what we're saying is if a diagonal creates two congruent triangles, then it must be a parallelogram. So that's the first condition of proving that it will have to be a parallelogram.